Awesome. So hello,
Cool.
everyone. Thanks for having me. I will be talking today about interpretable self-aware neural networks for robust trajectory prediction. Before I get started with the meat of the talk, I wanted to introduce myself a little bit, give a little bit of background for who I am. So currently, I'm a research scientist at the Toyota Research Institute, or TRI. I have recently finished my PhD at Stanford in Professor Michael Kokendorfer's group. Before that, my alma mater is the University of Toronto. Generally, my research interests are at the intersection of robotics, machine learning, and human behavior modeling. The tools and themes that permeate my research thus far, at least, are prediction, mapping, sensor fusion, uncertainty estimation. So the agenda for my talk today is going to be first a short shout out to the work happening on the team I'm on at TRI. Then I will give a brief overview of my work at Stanford as a whole. And then I will deep dive into interpretable out of distribution detection for trajectory prediction. That will be sort of the meat of the talk. Before I go on, I guess it's fair to say, if you have any questions along the way, please just interrupt me. Cool. So let's get started with a quick shout out to TRI. Like I said, this talk will mostly be about my work at Stanford. However, I wanted to give a quick overview of what we do in the machine learning division at TRI. The ML division is organized into two main research departments, focusing on computer vision and interaction. Our approach to learning is based on using self-supervision, both for perception and reconstruction, and specifically on discovering and using fundamental learning principles, which allow us to learn and scale learning with data, ideally without human annotations or with as few as possible. At the other end of the spectrum, we have learning how to act in the world by observing or by imitating humans, where safety is one of the most important aspects that we consider. One of the areas where the team has made really exciting progress recently is in deep neural networks for general perception. On the left here, you see an example of the team's 3D object detector that just runs on camera images. One or multiple cameras can be used and positioned around a vehicle for extra coverage. The team has set a new state of the art in the field, and one of the key insights that led to this was a new end-to-end architecture that goes directly from images to bounding boxes. On the right here, we have a second research direction where the team has been making a lot of progress as well, and that is tracking from images and LiDAR. The team has been studying concepts like object permanence, which is the idea that an occluded object or obstacle doesn't disappear if it goes out of visibility. It still exists and may reappear again at some point in the future. Another important research direction for us is reconstruction, and where we've made progress in two directions, the modeling of objects and scenes. On the left, we have the output of ROAD, a paper recently presented at CoRL, which stands for Recursive Octree Autodecoder. With ROAD, the team was able to model more than 1,000 objects by projecting them, all of them, into a shared structured latent space. This led to a high degree of compression, up to 99%, when comparing to the size of the neural network with the original object models. And they still retained about 99% of the reconstruction accuracy. Finally, on the right, we have an example of depth reconstruction from the Kitty data set. What we see here is an output of our mono depth system, which is monocular depth estimation, where you're trying to predict the depth from camera pixels, essentially. This runs only on images and outputs depth. And it can also output camera poses and calibration. The team is constantly evolving the system and scaling up to multiple cameras, uncalibrated cameras, multiple tasks. The backbone's constantly evolving from sort of more traditional CNN style backbones to recent breakthroughs in ML, such as transformers. Our team is also—
Can I ask one question? Sorry.
Yeah, please.
Regarding this road work, so compared to what does the compression ratio, compared to what is the compression ratio calculated?
Yeah, so this is our computer vision side of the team, so I'm not going to be super accurate. I do recommend
no problem.
you read the paper if you have detailed questions, but generally 99% like the neural network size as compared to the original object model. So yeah, that's as much information as I have for you. So if you want to get more details, please do read the paper. It was at CoRL in December.
Right, I'll check it out. Thanks.
Yeah, of course.
Maybe I have another question also.
Yeah.
So
sure.
I was just wondering, so all these research papers, are they also applied already in Toyota products, so to say, or how does
some of them are currently being so in progress. Yeah, they have a lot of transferability going on internally across many teams, especially the more sort of developed works.
Okay, makes sense. Yeah, thanks.
Yeah, no worries. And then finally, this is the team that I'm on, and this is some of their work highlights. So the focus here is on learning from interactions and how to do this safely. We have looked at how to evaluate reward functions from a dynamics-aware perspective and how to consider agent interactions during motion planning as well. We have also done work on robust prediction and planning, particularly when dealing with uncertainty as well as risk. This is important as we want autonomous agents to be able to quantify risk and uncertainty in a principled way, such that they may take the most reasonable action while maintaining a high degree of safety when operating around humans. And this last bit is most related to what I'm going to talk about in my talk. So at this point, I'm going to switch over to an overview of what I did during my time at Stanford. So taking a step back, we see that recent algorithmic and hardware advancements in robotics have yielded extremely impressive results in fields like transportation, search and rescue, personal robotics, and that's just skimming the surface. However, modern autonomous systems still have challenges operating in complex human environments, such as an autonomous vehicle in a cluttered, dynamic urban setting like this scene in New York City. The key sort of insight that has fueled my research philosophy at Stanford is that in order to achieve a future in which robots exist synergistically with humans, robots must make uncertainty and socially aware spatiotemporal inferences about human behavior. Focusing on autonomous prediction and perception, I have considered 4 different challenges in this space while at Stanford. The first of these is how do we predict the evolution of a cluttered environment in time? This can be difficult since human behavior can vary drastically from person to person. And in cluttered settings, there are computational and visibility limitations as well. So this first series of works proposes an end-to-end recurrent framework that uses a map-centric occupancy grid representation of the environment to make spatiotemporal predictions. Spatially, robots need to be able to handle partial observability of their environment due to physical occlusions. These can occur from sensor limitations, from other agents obstructing the field of view. Humans are actually really good at extrapolating from their experiences by making inferences from observed social behaviors. Following this reasoning, we propose using observed human behaviors to infer occupancy in occluded regions around the robot. In this way, treating people as additional sensors. In order to safely integrate human behavior modeling into the robot autonomy stack, the perception system must efficiently account for uncertainty. For example, in a trajectory prediction task, given a straight path trajectory, a vehicle may continue straight or make a turn in the future. Capturing this multimodality in a tractable manner was the focus of our work here. We proposed a means to sparsify the discrete latent distribution in a deep generative model for trajectory prediction. And we did so without compromising its performance. Finally, the perception and prediction system should be able to capture the uncertainty associated with out-of-distribution scenarios, which may be encountered in the real world and maybe were not present during training or during development. Here, we're proposing to accomplish this for trajectory prediction by learning parameters for a second-order distribution, such as a Dirichlet, over a low-dimensional and interpretable latent space. So all these contributions can be categorized into sort of two sections: spatiotemporal perception in human environments and uncertainty-aware machine learning models for trajectory prediction. Given the theme of this reading group, zooming into the uncertainty-aware methods, we consider aleatoric and epistemic uncertainty in the context of a trajectory prediction task. Aleatoric uncertainty results from data uncertainty and is irreducible. An example is two equally valid predictions given an input. Epistemic uncertainty, on the other hand, arises from how well the model represents the data and from data distribution shift. For this talk, I will dive into a project focusing on epistemic uncertainty estimation for trajectory prediction. And this brings us to sort of the meat of what I'm going to talk about today. So before we get started, we want to think about why modeling epistemic uncertainty is actually even important. Neural networks can often be overly confident in their predictions when faced with out-of-distribution inputs. This can cause issues for safety-critical systems like autonomous vehicles or robotics as a whole. For robots, it's important that a prediction module can provide a level of confidence in its output to a downstream planner. To identify out-of-distribution inputs, we want the network to estimate a level of its own confidence or epistemic uncertainty. And this is what I call a level of self-awareness. Unfortunately, there's not currently much work in the space of epistemic uncertainty estimation specifically for trajectory prediction. And existing methods from the machine learning community are often applied to sort of small benchmark problems, require explicit out-of-distribution data during training. It's often not possible to have explicit out-of-distribution data during training time, especially for real-world systems with high-dimensional inputs. It's just not realistic. And lastly, something that maybe doesn't matter as much when you're dealing with small data sets like MNIST is the lack of the interpretability of this uncertainty estimate. And this becomes important when you're dealing with these high dimensional inputs, like, for example, is the case for trajectory prediction. So this leads us to the research question: how do we meaningfully and tractably capture epistemic uncertainty for trajectory prediction? We attempt to begin to answer this question in our recent paper presented at the Conference on Robot Learning, or CoRL, this past December. So Dirichlet distributions can model the higher order epistemic uncertainty over a classification task. Learning Dirichlet parameters for epistemic uncertainty estimation is called evidential deep learning. The problem with a lot of these methods is at least in their original formulation, is the need for explicit out-of-distribution examples during training. This is not a realistic assumption, as I mentioned earlier. Recent work by our very own Bertrand here has proposed bypassing explicit OD examples during training with the use of deep generative models. So one such method is posterior networks, or PostNet, which is an evidential deep learning approach that uses normalizing flows to learn a posterior distribution over predicted probabilities. PostNet considers a classification task and learns a Dirichlet distribution over it. So it computes the parameters for a Dirichlet distribution, which encompasses the epistemic distribution Q and the aleatoric categorical distribution, which we term P bar, for an input X. So what this looks like is we have a distribution Q parameterized by the learned Dirichlet parameters alpha. We have P bar, which is a categorical distribution parameterized by the average of these alpha parameters per class. The alpha parameters in turn consist of two parts, prior and learned beta parameters here. As per Bertrand's paper, and we use a uniform prior here, which makes things simpler. The beta parameters are constructed as follows. So we have NC, which is the data count in the training data for the class C. R is a normalized probability density learned using normalizing flows over a low dimensional latent encoding Z. And this is again per class. It's important to learn this normalized probability density over a low dimensional latent space Z to ensure that we're still tractable with normalizing flows and that the learning for them is relatively stable. So this brings us to our contributions and how we build on PostNet. So what we do is we propose a novel paradigm called Interpretable Self-Aware Prediction, or ISAP. ISAP uses evidential deep learning to estimate the epistemic uncertainty in one shot for trajectory prediction. We introduce interpretability into the uncertainty estimate by distributing it over interpretable low-dimensional latent variables. We were able to demonstrate superior uncertainty estimation performance of ISAP over state-of-the-art approaches on the new scenes data set. And if you're curious, our code is available online from this link. Cool. So since trajectory prediction architectures often use a discrete encoding to capture the multimodality in the predictions, the epistemic uncertainty can be modeled over this classification task using a Dirichlet distribution. So we can directly apply PostNet to this discrete anchor space, which is sometimes latent and can be learned with things like k-means, or is sometimes just the output of the neural network. So PostNet doesn't have this element of interpretability. It just has a latent space, latent encoding that's just low dimensional. What we wanted to do is infuse some interpretability into this latent space. And we do so by encoding an input X into 3 separate latent variables representing the agent's past behavior, road structure map, and the social context surrounding the agent of interest. So this figure shows the inputs and outputs of our proposed architecture. So the encoders take as input this input representation. And I want to take a moment here to look at this representation and realize why we need the interpretability. So if I say that this input is highly uncertain, I don't know what to do with that as an ML engineer or even just within the system. Because I don't know if this uncertainty comes from, maybe there's a traffic cone that is causing really weird social behavior that we haven't seen in our training data. Maybe we're in a new city and there's a road configuration we haven't seen before. Or maybe there were some issues in terms of control, or some of the sensors failed, and maybe the past trajectory of the agent we're trying to predict for is a little wonky. So figuring out what the source of the uncertainty is actually really helpful here. just because of how complex the input is. So we take this input and we encode it. The output is 3 Dirichlet distributions over the agent behavior, the map, and the social context. The latent spaces are self-supervised by splitting up this input, as I'll show shortly. These are the decoded sort of elements of that. Yeah, any questions on this point? I will have a more detailed architecture on the next slide.
I don't have any questions yet. I guess I'm quite curious to see like the full architecture part. But maybe one question a bit related to the use case in general would be, could it be that the robot that you learns like some good uncertainty estimates, but does not achieve like reliable goal, so to say. So the goal is, so it learns like a bad goal, but it has good uncertainty estimates on this bad goal. So it's maybe a bit vague question, but maybe you have some input on this.
Yeah, so I think goal-aware epistemic uncertainty learning is super interesting and is actually part of my future work. So super relevant question. I think there are lots of interesting connections there, particularly with offline RL and more broadly with foundational models, pre-training, all sorts of things like that. I think there are lots of interesting questions there. This work in particular, we were just handling trajectory prediction. So we didn't really think about sort of goal conditioned uncertainty estimation, if that makes sense. But I think that's an excellent question and a really sort of good research direction moving forward.
Makes sense. Thanks. Yeah.
Yeah. Cool. So zooming out a little bit, this is the full architecture. We start with our input representation. It gets passed through a backbone. This can be a ResNet of any kind. And then it gets split into 3 different encoders to have our 3 different categories of latent variables. This achieves Z agent, Z map, and Z social context. Then we have normalizing flows, which learn a normalized probability density over each of these latent spaces per class. So basically everything is multiplied by 3 here. And then we have these decoders that produce the self-supervision and induce the interpretability into the architecture. And we can do this in a self-supervised way because we can just split up programmatically the input representation to have sort of the past trajectory here be decoded. This is just a vector. I visualize it as an image, but we just use it as a vector. We have the map decoding and we have the social context decoding. From the normalizing flows, we achieve all our alpha vectors for our Dirichlet distributions, and then we can combine them together and sort of still be able to do our prediction, which will depend on this discrete anchor space, and also get an overall epistemic uncertainty estimate and sort of a broken down epistemic uncertainty estimate as well. The loss ends up being a variation of, pun not intended, of the elbow loss plus 3 reconstruction terms in order to enable the self-supervised portions of the architecture. Any questions here?
Maybe one question would be, would that be, so why is there only 3 Dirichlet distributions? So to say, why is the split only in terms of agent map and social context? Could it be that there are some others? I don't know. Interesting.
Yes, definitely. We went with this because intuitively it sort of made sense, and prior literature sort of used this kind of interpretability split for prediction architectures as well. Something that is not explicitly analyzed here is what happens if there's sort of interaction between these different categories. There is some level of it because they all share a backbone, and I'll show some examples to show some inkling that there might be some, but explicitly figuring out how to model sort of the interdependencies, because, you know, the social context is going to be affected by the map and so on, that would be something that would be good to explore in a future work as well.
That makes sense. Okay.
Cool. I'll start getting into some results then. So the way we set up our experiments, we wanted to use real world data. So that's our new scenes data set. But we had to modify it for the OD detection task. To my knowledge, there was no such existing split at the time. So I spent a large portion of this project figuring out splits that make sense. So what I came up with are two. So one is based off of the input pass trajectory, and one is based off of the map. So for the first one, we consider slower input trajectories as in distribution and faster ones as out of distribution. In the map-based one, we have small roads with no roundabouts from Singapore as in distribution and roundabouts from Boston as out of distribution. So onto some results. First, we want to make sure that we can still perform our original task of trajectory prediction with the proposed epistemic uncertainty estimation modifications. So the baseline trajectory prediction model that we use is called CoverNet. It actually came out sort of from Newtonomy. It was sort of originated from New Scenes as well. We also look at ensembles of CoverNet of sizes 5 and 10. Post-CoverNet is the proposed ISAP architecture if you delete the interpretability part. So we just have one latent variable Z. So everything is as it was in PostNet with some modifications towards CoverNet. And what we can see here is that although the ensembles generally perform sort of better as a whole, as compared to CoverNet original as well, our methods are fairly close in performance, which is good to see. So we don't lose a ton of performance by adding this sort of extra elements to it. This is an important table because we wanted to make sure that the chosen out of distribution split that we consider is actually difficult to generalize to for the original CoverNet model. And here we have in distribution metrics first, so these ones. And then in parentheses, we have the out of distribution data metrics as well. The metrics here, I forgot to mention on the last slide, but they're average displacement error and final displacement error. These are sort of traditional trajectory prediction metrics, and lower is better for all of these. So what you can see is a drop in performance when going from in distribution to out of distribution for both of these cases, which is what we want to see, because that means that detecting inputs that are out of distribution is actually important here, because the network would not be performing as well as it should.
So maybe I have one question.
Yeah,
so this is the results for CoverNet, right? Did you look also at this generalization capacity for ensemble?
Sorry, say that again.
For ensembles, I was just wondering if maybe you see like a better generalization for some reason.
Yeah. I mean, you do to some extent. So I didn't look exactly at these metrics for ensembles, but I do sort of the sweep of uncertainty metrics as a whole. Yeah, I don't think I have exactly this table for ensembles. Yes, they will generalize slightly better, but so should post-CoverNet as well, and ISAP as well. So what's sort of important now that we know that sort of the model without the uncertainty estimation of like any kind in terms of epistemic uncertainty fails. So we need some sort of epistemic uncertainty. What kind? It depends on how well they perform. So this is how well they perform. Lots and lots of numbers here. So the table is split up into the two experiments, input pass trajectory on top, map-based experiment on the bottom. This table is really focused on the epistemic uncertainty estimation and calibration in general. Following the post-net analysis, we use area under the receiver operating characteristic, ORC, and average precision APR to compute the confidence calibration in the predictions. So here, higher is better. So these 4 top numbers is what I'm talking about. The confidence for correct predictions, which are labeled 1, and we have low confidence for incorrect ones labeled 0, or that's the ideal case. We also consider some other metrics like expected calibration error, the Breyer score, and then again, following sort of what post-CoverNet did to evaluate OOD detection performance, we use ORC and APR with labels 0 for out of distribution examples and labels 1 for in distribution data. To provide further sort of intuition for post-CoverNet and ISAP, we also report the ratio of average sums of the Dirichlet parameters for in distribution and out of distribution data. So that's this last line of metrics here, where lower is better in this case, because there's more of a distinction. So across the majority of the metrics, ISAP outperforms. This is particularly clear in the input trajectory experiment that we see here. In the map-based experiment, things are less clean. Part of the reason for this is the out of distribution data split. The metadata that I use to do the split is provided for a scene rather than a single time step. So when I choose roundabouts to be out of distribution, that also still includes straight road passages leading up to the roundabout as well. So that's part of the discrepancy here. But what was nice to see was that in the out of distribution detection metrics, we still like solidly outperform. And these are sort of the metrics that we found to be most reliable as I was sort of trying different things as well. Any questions here?
Actually, I would have one question. I have one question is, I guess you mentioned that you learn like 3 Dirichlet distributions, and here you use, I guess, the sum of the uncertainty of all of them, so to say. If you just use one of these Dirichlet distribution, would you see that a specific Dirichlet, like a specific Dirichlet distribution indicates that it's OD, meaning that we have also maybe the reason why the model is uncertain?
Yeah, so I tried some like early experiments with that, and I did see a trend for that. I don't know how fully meaningful it is. So like I can show you some qualitative examples. So for the input pass trajectory experiment, if I used the agent Dirichlet distribution, it was pretty solid because there's a very direct sort of, it's very clear where the uncertainty is coming from, the input pass trajectory. So the agent trajectory was the most important sort of latent there. This one was a little more interspersed because I think here you have more interconnections between, okay, the map affects the social context and it also affects the sort of the past trajectory of the agent. So there's different elements coming in there. So there the performance was more kind of diffused, I would say. For the agent experiment, it was fairly clear cut, which was kind of as expected.
Okay, makes sense. Thanks.
Cool. I'll show some pictures now. Okay, cool. So some qualitative results for the ISAP framework. This is on in distribution on the top and an out of distribution example on the bottom, and the input pass trajectory experiment. We see that the ID or input in distribution example has a slower moving trajectory. So this red trajectory is shorter than this one. So this is what, you know, should be representative of the data set. And what we're looking at is the sum of the Dirichlet parameters alpha 0, which can hopefully give us a sense of certainty in the predicted categorical distribution. So we expect higher alpha 0 values for in distribution examples and lower ones for out of distribution. So ISAP learns the epistemic uncertainty in the agent behavior latent variable to be higher for the in distribution case than the out of distribution case, which is what we want. In the examples shown here, there's a very clear difference between the alpha 0 values in agent, which we expect and we're happy to see. The map latent variable indicates that big multi-lane highway style roads are less likely for slower input trajectories than intersections. So this is sort of the discrepancy that we're seeing here. For the social context, the alpha 0 values are actually quite similar and also higher. A potential reason for this could be that slower trajectories would usually occur in traffic. And in both scenes, there's a large number of cars surrounding the predicted agent. Overall, what we wanted to see was that, the alpha 0 agent value shows a very big discrepancy, which it did, and we were happy to see that. So these are some videos showing some more examples here. In distribution is on the left, out of distribution is on the right. Once again, we have sort of a slower trajectory on the left and a faster one on the right. My cutoff for what was in distribution versus out of distribution was 10 for this distance. So this is solidly out and this is solidly in. Yeah, so basically we see sort of what we expect. And what's also kind of interesting is that you can see CoverNet fail a bit more over here at the higher speeds in terms of not predicting correctly. These are the top 3 most likely modes in green, and the black is the ground truth. Cool. So now looking at the map-based experiment. Again, same deal. We have in distribution at the top, out of distribution at the bottom. We see that our in distribution example has sort of a smaller going into a straight road, and our out of distribution example has a roundabout in it. The map variable clearly shows a distinction here between the alpha 0 values for in distribution and out of distribution. And again, some videos. So what's happening here, again, left is in distribution, right is out of distribution. We see that the in distribution example has a straight, smaller road that comes out after an intersection, while the out of distribution example starts with a straight road and goes into a roundabout. The alpha 0 values to pay attention to here are the map alpha 0 values. So what we see is that ISAP learns the epistemic uncertainty in the map latent variable to be higher for the roundabout, which we sort of hope or expected. It is interesting to note that the big intersection in the in distribution case is high uncertainty, as big roads should have technically been filtered out of the in distribution data. And this is sort of another example of the artifacts of the metadata that I had to use to sort of do these splits. Last sort of set of plots I wanted to show is a sanity check that the learned alpha values reflect reasonably the true data distribution. So the learned Dirichlet parameters should serve as pseudo counts for the data. We do this for the input agent past trajectory experiment, as we can plot that. The x-axis on the plots represents a heuristic for the trajectory speed. I basically looked at the distance between the most recent and the oldest waypoints, and that's sort of the 10 number that I used to decide if something was in distribution or out. Although the scales are obviously different on both plots, we see similar patterns in terms of there's a lot of data where cars are stopped, which you can see by this peak here. And then there's another peak here around 5-ish that is sort of similar in shape here. And then once we get into, we pass this sort of 10 threshold, we really get into out of distribution land and the certainty falls off. Any questions here?
I like a lot this visualization, especially like the one that you showed before, because I don't know, I think it's pretty convincing in terms of interpretability. So yeah.
Thanks. All right, cool. So just to conclude here, before I talk a little bit about future work. So we proposed ISAP, an interpretable trajectory prediction paradigm that estimates epistemic uncertainty in one shot using evidential deep learning. Our approach maintains trajectory prediction performance and outperforms established techniques like ensembles in uncertainty estimation. Some limitations, I found normalizing flows to be very brittle and struggle to scale to larger latent spaces, which prevents their representational capacity. And especially when I'm dealing with high dimensional inputs, I felt pretty limited by the latent space that I had. I actually had to decode one layer sort of up from the latent space. So I had more representational capacity to pull from to have the decoded images sort of look nice. We also, of course, impose an inductive bias on ISAP for autonomous vehicles in this setting. So if this was to be repurposed in indoor robotics, for example, or any other domain, the interpretability structure may have to be adjusted as well. And lastly, there was a small gap in trajectory prediction performance for ISAP, which it would be great to work towards closing in the future. So going back to sort of my key insight at the beginning of the talk and my general sort of how I approached my PhD. So in order to achieve a future in which robots exist synergistically with humans, robots have to make uncertainty and socially aware spatiotemporal inferences around human behavior. So we want these methods at sort of the intersection of robotics, machine learning, and human behavior modeling to engender safe and socially acceptable human-robot interactions. And these ideas have the potential to make impact in a number of domains that involve human-robot interaction. Autonomous driving has served as a test bed for the majority of my work at Stanford, but these ideas, I hope, are more broadly applicable. And in particular, I am currently interested in how these learnings transfer to the domain of indoor assistive robotics. And some research questions that I'm considering are around epistemic uncertainty and contingency planning, goal conditioning, the learning of the epistemic uncertainty, and this goes back to the point Bertrand made, and how the epistemic uncertainty fits into frameworks like learning from demonstrations. And the idea here is that hopefully robots will reason about human behaviors in order to achieve their goals, either alongside or in collaboration with humans. And that's all. If you have any last remaining questions, I'm happy to take them.
Yeah, well, I have one question about the flows. That's an interesting remark, that they are brittle. Did you try something else, or did you already have some ideas?
Yeah, so I tried GMMs like Bertrand did and found them to work worse. So I sort of, I kind of just, for this paper, I figured out, parameters that made it work, that sort of made sense, but it was a pain to work with, and they also slow things down. Do I necessarily have a better idea right now? I don't think I would say that, but, there are some opportunities to try something else. Maybe variational autoencoders would work better in this case, maybe not. It's a trial and error kind of situation in my mind, unless something huge happens in the field and really puts everything on its head. I'm curious if you have better tools that you know.
For me, to be honest, like with these kind of methods, GMMs always work well, but I mean,
I found a solid drop in performance with GMMs. So
maybe if you have it in this end-to-end learned setting, it's a bit different.
Maybe
because I mean, you need to update the parameters of your GMM model, and that can be tricky. I guess. I mean, depending on how you parameterize it, like it can be unstable. So then, but for me, GMMs work, but only when I train them post-training. and only when I do it on a pure classification or semantic segmentation task. So as soon as I have some regression in there, I mean, the assumption also doesn't make sense that you have clusters in your latent space.
Yep.
Then it never worked. But I mean, usually for me, if I would have to have an uncertainty estimation method that works, I always use ensembles because they just work. I mean, they're
so ensembles are really great for a number of reasons in terms of like easy to implement, sort of like a first try thing, and they're fairly reliable. What I found interesting here is, so for some of these performances, it wasn't always clear that a bigger ensemble was better. So there were times where like the smaller ensemble was winning out. And even when I was looking at like trajectory prediction performance, so for this experiment, most of the wins are in the smaller ensemble. So that kind of creates some, I don't know, unsatisfying questions for me in terms of like, how do you decide the size of the ensemble, first of all? Second of all, I mean, they do add to the computation, right? So if you're looking for something one shot that's getting closer to real time without having to like run 10 models at once, I think they lack there. But generally, I totally agree with you that they are a good first try for sure.
This is really strange here. That I mean, I would expect it to be best if n goes to infinity.
Yes, yes.
But,
okay, not the performance that I found, at least consistently. So, you know, I mean, it can be luck of the draw as well, right? If there were some bad seeds in there, but yeah, overall, this was not the performance I observed. And this might also have to do with how well the original model sort of is able to train, like what its capacity is. Because if the original model is not that good, estimating epistemic uncertainty gets weird, right? Because there's some, like, a lot of things are epistemic uncertain then.
Yeah, that's true. Yeah, I also made this observation that when you have if you have a model that performs better, then your order of distribution detection also becomes better, which is weird, but I mean, you have to live with it. I don't know. So maybe one question, how do you separate aleatoric and epistemic uncertainty for the ensemble?
Yeah, so we did basically the same thing that Bertrand did. So yeah, we looked at sort of I think the 1 over variance. Let me see, I have some notes on this. I always forget. Yeah, so for the epistemic, it was 1 over the variance of the predicted class probability across the ensemble. And then I forget for the aleatoric. Bertrand, can you help me out if you remember how you did that?
So if I recall correctly, like each ensemble predicts somehow the mean and variance, right, of Gaussian, and we just mean the variance of all the ensembles, and this gives like the aleatoric variance, so to say.
Yeah.
So basically, similarly to so this is not for, so okay, the example I took was for regression, but actually yeah, for classification it would be the same. Just mean the categorical distribution, so to say, take the mean of the categorical distribution, and this gives like a mean categorical distributions, and then we take the variance of the entropy of it, or the variance of it.
Oh, okay, got it. Yeah, basically, I think I know that one. Yeah.
Looking at the expectation of the distributions versus looking at the spread of the distributions.
Yes.
Yeah,
exactly.
So looking at the spread of the margin versus looking at the margin of the spread.
Yes.
Okay. Yeah. Cool.
I don't know if you have any trick to make this work better.
No, actually not. But it was something that I was thinking about. Recently, like the last half year, I always circle back to it, but I don't know. I don't have a solution because I found that it doesn't, like, the separation doesn't really work all that well. I mean, I don't know whether you had the same observation, but like for me, Like I accidentally ran into this when I was trying it for different model capacities, and I was getting really strange results that, like, depending on the model capacity, there was more aleatoric or more epistemic uncertainty. And I don't know, I don't have a solution for it, but it's like, if you have the perfect model, it works.
Which is a problem.
Yeah, which is the problem, yeah.
Yeah, I think that's also kind of an open thing, and everyone sort of tries their own thing, and I'm not sure that there's a convincing decision for one way or another.
Right.
Lots
Absolutely
of
agree.
open problems, which is great for us.
It's good for researchers, yeah.
Exactly.
Good
All right.
stuff.
I might have just a last question,
Yeah.
if I can. So I was wondering, so if you know many papers that does this combination of uncertainty and interpretability, similar to what you do, because sometimes I guess it's indeed like hard to know why the model is uncertain. So if you have, I don't know.
You know, honestly, I don't, because I looked and I really looked. There were usually, if you're doing robotics and out of distribution detection, what I've seen is ensembles and MC dropout. If you go into the machine learning side, there's sort of more variety and like more different things. The only times I've seen the interpretability structure were in sort of like just doing trajectory prediction rather than doing epistemic uncertainty estimation in particular. Yeah, but most of what I've seen in the robotics space is one of those two ways, because like Yana said, it works, right? Ensembles generally work. There are downsides, but they are simple to implement. So I think a lot of people don't go past that. Yeah, if I come across anything, I will definitely let you know. But as of right now, not too much. But it is nice in terms of, I feel like when I started with this, there was really not a lot of anything out of distribution in the robotics space. And it's not like, you know, a ton now, but it's growing. And I think there's more and more interest in this, which is great.
Yeah, it makes sense. Yeah, thanks.
Cool. All right. Thanks for having me.
Thanks a lot.
Yeah, thanks for the chat. It was really interesting.
Yeah, it was great talking to you. Bye.
Thanks a lot. Bye.
All right, take care.
You too.